Good afternoon, ladies and gentlemen, and thank you for joining us. My name is Kris Michaels. I'm the Director of Communications here at SimSpace, and I'm proud to present today's Emerging Threat webinar. Today, we're talking about the threat of DirtyPipe, and I'm joined today with Matt Kiely and Kris Weber from our team. Both Matt and Kris are part of our cybersecurity content teams, and each of them will provide both an offensive and defensive perspective on the threat today. Matt is a seasoned practitioner with 10 years of experience in IT and cybersecurity. He's worked as lead cybersecurity analyst at the MIT Lincoln Laboratory, red team operator and exploit developer at a large financial institution, and principal cybersecurity and content architect and instructor here at SimSpace. He's also a decorated United States Marine. He holds a Bachelor of Science Bachelor of Science in IT from Northeastern University and a graduate certificate in cybersecurity from Rochester Institute of Technology. He also maintains an alphabet soup of active professional certifications. Kris Weber is a former Army infantry Army infantry and cyber officer who both walked in the woods without using his brain and sat at a desk without using his muscles. He joined SimSpace having previously served with U.S. Cyber Command and now serves by developing cybersecurity labs and challenges for our training content team. He's a graduate of the United States Military Academy at West Point and has also received an alphabet soup of cybersecurity certifications. As a disclaimer, while this webinar is designed to provide you with as much information as we have about DirtyPipe vulnerabilities and its exploits, the guidance that follows is based upon the information that is currently available. Should new vulnerabilities be disclosed and published with corresponding CVEs or guidance from affected applications and services, SimSpace will update its training content with appropriate information. And I'm told we are actually doing that as we speak because there's new detection methodologies that were put out there. For any additional assistance, we recommend contacting our customer success team at success@simspace.com. With that, I will turn things over to Matt and Kris and let you guys tell us, what is this DirtyPipe and why should we be concerned about it?
Excellent. Thank you, Kris. Hey, everybody. My name is Matt Kiely. I'm one of the principal security content architects here at SimSpace. I'm joined by my colleague, my friend, and a mentor, really, Kris Weber. Kris.
Kris Weber, happy to be here. Yeah, I've been developing content here at SimSpace for a little over 2 years. And yeah, DirtyPipe is exciting. Let's go to Matt to jump in and start doing the introduction, huh?
Sounds good. I will now share my screen. And you should see the CVE page from the National Vulnerability Database website on CVE 2022-0847, nickname DirtyPipe, which is the subject for today's webinar. So just briefly, let's talk about how this webinar is going to go. Right now, we're going to cover kind of the high level of what's really going on with DirtyPipe, kind of some of the high level details. We're going to go into the theory of how this vulnerability can be leveraged into exploitation. And then we're going to do some practical exploitation on ranges that we have here in SimSpace land.
And just a reminder for everyone, as you have questions, feel free to put them in the question module below. We will attempt to answer as many as possible as we go, and we will have a dedicated Q&A question section at the end.
Absolutely. This is very informal. I like to think of these as kind of a ride along. We'll be teaching you what's going on. We'll, entertain questions, and we'll try to, really kind of get to the bottom of what's going on with DirtyPipe in this case. And then once I'm done with the practical demonstration of the offensive perspective, so the technical exploitation, we'll have two demonstrations of that. And then I will give it over to Kris for the defensive perspective as well. And mitigations, that kind of thing, detection, all that good stuff. So like I said, today, subject is CVE 2022-0847 DirtyPipe. This vulnerability is brought to you by the letter C. This is a vulnerability in how the Linux kernel handles pipe memory structures. If you're not familiar with what a pipe is, you've probably used one if you're familiar with the Linux operating system. If you've ever echoed something and then piped it to another command, or maybe, catted out a file and piped it into the grep command. You're using pipes. Pipes are a method for inter-process communication on the Linux operating system, or the Linux kernel, I should say. So it's a method to get data from one process to another. Data kind of goes into one end of the pipe and out of the other end of the pipe. And due to an update in the Linux kernel as of May of 2020, so May 20th, I believe the commit was pushed to the primary Linux kernel repo. May 20th, 2020, there was a bug in the way that the pipes flags are handling certain structs of data. And in certain circumstances, you can get data that should be written to a pipe to actually, instead of just remaining in memory, be written down to the actual on-disk footprint of a file that you're trying to pipe around. If you notice that I'm looking over here, I'm also just reading my notes. Trying to catch
Matt,
up
I
on
think
where I am.
that particular commit was actually pushed by Linus Torvalds himself, wasn't it?
Yep, you can go see the commit history you can go right on GitHub and you can find the Linux kernel for that one. But let's read the description. So a flaw was found in the way the flags member of the new pipe buffer structure was lacking proper initialization in the copy page to iter pipe and push pipe functions. So two vulnerable functions that could be coerced into having stale values. Again, brought to you by the letter C. An unprivileged local user could use this flaw to write to pages in the page cache backed by read-only files and as such escalate their privileges on a system. What exactly does this mean? In certain circumstances, if you have a pipe that you can write with and a file that you should not be able to write with, you can get the memory page cache of that file via kernel system calls to write arbitrary data into a read-only file. And what does that mean in a practical sense? Linux privilege escalation if you have access to the server. So there are some limitations. There are some some limitations with how this exploit can be carried out. They prove to be rather trivial, but it's not really carte blanche. You can't really create a file and have immediate access or something. There are a few stipulations that you need to look at, but we will show a few proof of concept examples where those stipulations tend to be pretty easy to work around. This is rated as a 7.8 on the common vulnerability scoring system. It means it's pretty high. It's not remote executable or remote exploitable, I should say. If you have local access to this system, you will be able to perform this exploit on Linux operating systems, Linux hosts that are vulnerable to it. In the defensive section and the detection section, we'll go over the range of the Linux kernels that are affected by this. But notice how I'm saying Linux kernel. It's worth noting that this is a kernel vulnerability, and as such, any Linux operating system any host of the Linux operating system or any Linux derivative operating systems are going to be affected by this. And so that includes things like the Google Pixel, Android phones, among others. I've seen some proofs of concept now for phone operating systems that use Linux derivative kernels.
Hey, Matt, I think I accidentally stopped your screen share.
Oh, yeah. Okay.
By
sure.
trying to highlight you on the sidebar.
That's okay, because we're going to move it right over to the technical exploitation of this. So let's get this party started. So we got to think about how this is happening. The technical details of this can get very in-depth very quickly. This is a kernel vulnerability, and the exploitation happens at the kernel level. And I cannot claim to be an expert when it comes to that low level on the Linux kernel. What I can say is that the Sophos Naked Security write-up blog for this vulnerability, and even better, is the original write-up by the person who discovered this, by a gentleman by the name of Max Kellerman. Those are absolutely, they're must-reads if you're interested in really the technical details of how this is happening. So to summarize the vulnerability, a new flag was added to the kernel to allow the a new flag was added to the Linux kernel to be able to write memory into a pipe in Linux and then merge that into the on-disk file that pipe was backing. So data pulling from the page cache down into the actual file itself.
And Matt, to talk about what Max's kind of origin story of this a little bit.
Oh yeah, absolutely.
This is probably one of the, and you mentioned Max's write-up being a particularly good read. Totally agree. For one reason, it's maybe one of the most wholesome stories for a vulnerability discovery that we've heard. That pipe was detected by Max, and you can talk about this. Please go ahead.
Yeah, sure.
But in the course of his normal IT duties.
Yep. So a new flag added in that commit, the update to the Linux kernel in May of 2020, that did not introduce the vulnerability that actually gets leveraged by this exploit, but it did make it accessible and easier to actually exploit. The principal problem here is that there is a bug that was introduced in 2016 in a commit to the Linux kernel that allowed users to specify arbitrary flags during DirtyPipe usage. So you have now a new flag that allows you to pull memory page cache data down into the actual file that page cache is backing. And you have a bug that allows a user to specify arbitrary flags. The last thing that we have here is this interesting use of this function called splice, which is a Linux system call. So a system call is something that interacts with the kernel to be able to perform some kind of function. And splice is a way to be able to use pipes to kind of reduce the overhead associated with reading and writing data to and from files. When you combine those three things, if you have a pipe that you can write to and a read-only file that you shouldn't be able to write to, and you're able to use the splice command to open up the pipe to be able to write to the page cache of that file, and then finally be able to specify this flag that you can merge that data down into the actual file itself, congratulations, you now have Linux privilege escalation with a few stipulations. As Kris was just saying, I love the backstory. I'll take a very brief detour because the backstory here is hilarious. And it's just so good. Read that blog post. But the TLDR here is that Max was investigating trouble tickets for his company's platform, which is a platform called CM for All. And the trouble tickets were coming in such a way that there was a pattern to this issue that users kept experiencing, which was that their data was being corrupted. So there were these there was a piece of or a part of the platform was set up to be able to handle user logs, access logs, and wrap those up into zip file format. On Linux, you would have something like the tar utility to be able to do that, but they wanted to be able to translate that over to zip format as well. So they used the splice command to do this, to reduce the memory overhead of reading and writing files. So they're using pipes to be able to do this. And he realized that these trouble tickets kept coming in and saying, hey, my data in the zip file format is corrupted. And it took him, I think about a year, maybe, don't quote me on that, but it took him some time to actually figure out what was going on here. But he was able to very briefly, with just a few lines of code, reproduce kind of how the data flow was happening. You would read in from a pipe, you'd splice into another file. And then through that proof of concept, he was able to prove that he could send data through a pipe and use splice and have it written to a file that he shouldn't be able to write it to. And he figured this out by looking at trouble tickets. So phenomenal backstory there. Now, a little bit about exploitation theory. Like I said, there are a couple limitations to this exploit and how it would actually be used in practice. We can't create a file and we cannot cross a page boundary. So in memory, the page unit is 4 kilobytes, I believe. So 4,096 bytes, I think, if I'm remembering correctly. So we cannot cross out of, really what that means is that we have about 4,000 bytes of space to work with, and we can't create files. So one primary target for this is going to be a file like, we'll cat out etc pass wd. If you're familiar with the Linux operating system, you probably know what this file does. Among other things, it has kind of a list of the users on the server and their interactive shell and groups and some other information about them. What you may not know is that if you look at the root user here, so let's look at just the first entry in etc pass wd, this X right here means something very specific. Way back in the day, I believe Linux used to store the actual encrypted passwords of a user in this file. The problem is that this file is world readable. Keep that in mind. So somebody, I think at one point looked at this file and said, hey, it's probably a good idea to take the passwords, the encrypted password. They are encrypted, but let's take them out and put them somewhere else that's not world readable. And then we'll write something on the back end to be able to use those two files in concert. Thus was born the etc shadow file, which if you're an unprivileged user, you cannot read. You can't cat out the contents of that file. This X right here says, hey, there is no encrypted password in etc password. Go over to the etc shadow file and read it there. But what you also may not know about this is that if you were to replace this with an encrypted password, that would actually take precedence. And you can even leverage that by removing this completely and removing the need for a password at all. So there's some interesting things. Though I cannot write to this file as an unprivileged user, I can definitely read to it. So that's one of our criteria for privilege escalation via DirtyPipe. The second one is that I only have about 4,000 bytes to work with. what you're going to find is that the shellcode needed, really the exploitation, the amount of data needed to exploit this is not that big. All I really need to do is put maybe, I don't know the exact number, but it's about that many. What I've highlighted right there, you need to write about that much into the file to be able to exploit it. So it's not very much at all. Now let's move on to the technical demo of exploitation. So we know that we can leverage this exploit to arbitrarily write as an unprivileged user to a file that we shouldn't be able to. So what we're going to do is use the git clone, and I'm getting a little help from the autofill here, but we have just a little server in range to look like github.com, and we're going to pull the CVE off of github.com and take a look at what we're working with. I'm actually going to CD into that directory, and we're going to cat the contents of the first proof of concept that we are going to work with, which is POC wd right there, .c. I'll pipe that to less. So the exploit itself is really just going to write into etc passwd, and it's going to take an arbitrary value that we specify. In this case, we're going to just pass it an arbitrary password. It's going to encrypt that and then place that into the etc password file. Again, we're not going to need 4,000 bytes to do this. We're going to need much less than that. It will set the user info as pwned, which is a little funny. Of course, you could change that if you're looking to weaponize this more aggressively. You can change that. Arg v1, so the first arg passed in is going to be our the value that we're splicing right into that the etc passwd file. Let's go ahead and compile this. I will bring this up so it's a little easier to see. GCC, I believe I'm going to get a little help from the autofill here. The output is POC passwd. That's an arbitrary value I can specify. The source code here is POC password.c, lcrypt, because we're using the encryption library so that we can make an encrypted password and place it there. Looks like we compiled okay. Next thing that we do is simply run POC password with an arbitrary value that we can specify. In the module that we have on SimSpace and in this demo, I'm going to do woot woot w00t w00t. Hit enter. The proof of concept does its magic and it says it worked. Now all that I really need to do is sue to the root user, and I guess you're just gonna have to take my word for it. WOOT WOOT, with O's are 0 in that case. And on this instance of Manjaro, which is arch derivative, I am now root, and I can probably cat that flag.text. Who am I? I am the root user. Practically speaking, this means that if you have interactive access to a Linux server that's vulnerable to this exploit, trivial privilege escalation, when we go into the detections of this exploit, we're going to find that the indicators of compromise for this are a little sneaky, a little sneakier than your average privilege escalation. If you were to compare this to something like the last Linux privilege escalation that came out, PwnKit, it's less widespread, but much more surgical and much more sneaky, I would say. But I'll let Kris get into the details on that one when we get to the detection criteria, or the detection part of this. At this point, do I have any questions before we move on into the second technical exploitation demo?
Right now, there are no questions in the question module, but as people have them, please put them in there and we'll be sure to answer them as we go along.
Good. All right, so the first practical exploitation demo was over on Arch Linux, Manjaro Linux, really. We're going to move over to Ubuntu. Kris is a Manjaro and Arch kind of guy. I'm really more of an Ubuntu guy. It just works out because both of them are vulnerable to this in certain versions. So we're over here on Ubuntu, which I feel a little more comfortable in. And we are going to use the same technical exploitation proof of concept with a few alterations where we're going to take a set user ID binary and we're going to write the bytes of shellcode necessary to just spawn an interactive bin bash shell. So if anyone in the audience is kind of familiar with the, if any of you are OSCP or have done any technical exploitation in PrivEsc in the past, all you really need on a Linux system to be able to privilege escalate is to find something. In a lot of cases, all you really need to do is find like a set user ID binary that's running with loose permissions, and or maybe you write your own little set user ID, set group ID proof of concept, and you have something execute it at the root level. If you execute a shell, if I call bin bash, and you're not going to see it, it just kind of drops me right into the same thing. If you call bin bash from your current user context, that's the context that it runs in. So we can just exit out of that. So if I call bin bash using set user ID root permissions, it's going to run as root. So the way we do that is we are going to arbitrarily write, using DirtyPipe, a block of shellcode into any set user ID binary that I desire. Again, set user ID binaries, I should not be able to write to them as an unprivileged user. Well, turns out with this exploit, we can. So for this one, I'm going to get a little more, I would call it, apply a little bit more tradecraft, not too much, of course. And in fact, I'm going to just paste these in. These commands are a little bit long. Just basically, I'm setting up for the same kind of demonstration here. So git clone, and we're going to change directories right into that directory. We have the second proof of concept here, which is POC Trojan, I believe. Yep, that's it. And I'll bring this back up to the top of the screen. We're going to pipe this to less, and this is just an iteration, a kind of modification on the original proof of concept by Max Kellerman, but there's something I want to point out here, and here it is. We have two blocks of MSF Venom generated shellcode here, one for an x86 build of the operating system and one for a 64-bit build as well. We can't create a file and we can't write more than 4,000 give or take bytes, and the block of shellcode that we need is 54 bytes in length. So if you have arbitrary write for 54 bytes of memory, 54 bytes into any file on the file system, you can inject a block of shellcode that will spawn a bin bash shell. And again, if we did this in a binary that was not set user ID, nothing really would happen, but we can find a binary that is set user ID. Root will run with those permissions, and then we will get ourselves a root shell. So this demo is a bit more, I feel like I'm back in my OSCP days at this point. This feels a little bit more like what we would do with OSCP. Or maybe some of the other the kind of technical exploit certifications out there. So let's see what we need to do for this one. What we're going to need to do is find a good candidate binary for this. So I'm going to find from the root directory and then perm 4000 for the permissions necessary for the set user ID, and I'm going to pipe the standard error to dev null. I have a candidate binary that dev null isn't really a thing now, is it? So here we go. I have a candidate binary for this that I've already chosen, but this would be, if you wanted to go find set user ID binaries on a system in the first place, this is something that you could do. I'll just give this a moment to run. It's looking through the entire file system at this point saying, hey, is any binary in here a set user ID binary? Usually there are a handful. Oh, I must have typed something wrong. Interesting. Well, in any case, it doesn't really matter. So the binary I'm going to use for this one is going to be sudo, the sudo binary. So ls, we'll do la user bin ls la user bin. There it is. Read write set, that S right there is what we're interested in. Kind of makes sense, doesn't it? When you run things with sudo permissions, you need to elevate up to the root level. Usually it'll ask you for a password first and check to make sure you're in the sudoers file. But we're not going to do that this time. What we need to do is find the entry point of this binary. And I'm going to use a tool called readelf to do that and just set it as a variable value. So our hex address variable value is going to be the entry point of this binary, and this is going to be in hexadecimal format. So if we break open the binary with like a hex editor or a hex reader right now, we could go find the entry point by going to this memory offset address. Now, what I do need is to turn this into a decimal address. And so I'll do that right here. So we're just using Python at this point. If you didn't know this, this is pretty cool. You can use the print method in Python and just pass it a value in hex, and it'll print it out in decimal value. So we hold on to these two values. We've got 0x8880. That's the hexadecimal memory offset of the pseudo binary for the entry point, where the binary actually, when the operating system says, all right, pseudo, all you, go ahead, that's where it starts, right? And we have that in decimal as well. So like all good kind of red teamers here, we probably want to check our work a little bit and make sure we don't mess anything up. So I'm going to actually copy user bin sudo over to sudo.back. All right, looks good. Just in case we mess something up and we want to revert, we can do so. And actually post exploitation, we can move it back as well. Same kind of compile here, GCC-O, we're going to call this POC Trojan. And we're compiling POC Trojan.c. There we go. So if I ls right now, I'll do an ls-la. If I ls-la, we've got POC Trojan right there. The first argument is going to be the binary that we want to clobber here and inject the shellcode into. And the second argument is going to be the decimal value of the entry point. So what I can do is /POC Trojan. We do the binary itself, so user bin sudo. We did the backup. We have the backup in the current working directory just in case things go wrong. And I still have the decimal address, but if I just scroll up a little bit, I should be able to find it right there. So I'll just copy that. And so what this is saying is go ahead and open up the pseudo binary, use the DirtyPipe exploit to write the bytes of the shellcode into the entry point of that binary. If all has gone according to plan, if I now just call user bin sudo, if the demo gods are kind, and today they are, I have root on the system. Who am I? And now that I have root on the system, I'm free to do whatever I want to this, but I think I'll just call it a day after catting contents of, well, in this case, root flag.txt. And that is how you would use arbitrary write to inject the bytes of a simple bin bash shellcode into a set user ID binary of your choosing. One more thing that I wanted to show, because I think it's pretty cool. We're going to, just like I said earlier, we did, in fact, we don't even need to be in the root context for this one, but we'll do a hex dump xxd. And we're going to go find user bin sudo. And if bin bash is called, certainly that exists somewhere in the bytes of the program as a string. And so what I want to do is grep bin bash. Oops, got a little keyboard chatter there. Bin bash. What did we say? Let's echo out the hex address. What did we say the hex address was? 0x8880. We're right about there, 0x88A0. So we're right in the realm of where the entry point is going to be, and there is our call to bin bash itself. And that is how this exploit works. So at this point, do I have any questions?
Hey, Matt, while we're waiting for questions, do you want to do the cleanup step?
Yes. So I didn't actually record the timestamp on this. So what you would want to do at this point, because I didn't record it, it's going to be a little hard to guess when the copy over of sudo was. But what you would do is effectively you would want to, I can exit out of the root shell for this one. After I've established persistence or maybe installed a rootkit or done really whatever I want to do with it, you're going to want to move the sudo.back to user bin sudo. You know, I probably do need root permissions now that I think about this. Well, that's no problem, as we've just seen. We'll move sudo.back to user bin sudo. And at this point, there has been a time change in the sudo.back file and the user bin sudo file. So if there was a, let's say some kind of EDR was taking timestamp deltas between when a binary was written and when it was created and when the last time it was modified, there would be a change between that. All you would really need to do is before running the exploit, you would take a measurement of the timestamp of the file and then just write that with the touch-t command, I believe. I can't quite do that here because I forgot to do it at the outset here, but
that is. I just did it in the
Yeah.
background on the Manjaro machine by making up a date. So
Sounds good.
yeah.
Well, that concludes the technical exploitation demo of DirtyPipe. Do I have any questions at this point?
There's only one question, and it's actually for me, which is for people looking to receive their continuing education credits for ISC squared. Be sure to answer our survey at the end of this, and we will submit your ISC number on your behalf to make sure that you retain the credits for today's webinar.
Cool.
I guess in that case, we're ready to move on.
All right.
That's right.
That concludes my demo. I will kick it over to Kris for the defensive perspective. Kris, do your thing, man.
All right, my turn. Defensive perspective is patch, and we're done. All right, let me share my screen. And I just want to kick this off by showing what the module that we created last week for this emerging threat looks like in our platform. For those of you who aren't familiar, this is what a module, what we call them, a lesson basically in our platform looks like. It contains all of the text of the walkthrough and the explanation basically that Matt and I are walking through today, with the added ability to execute all of these demo things in the range right now. And so I do wonder, proper data sanitization. Didn't memorize which one this is. Oh, yeah, there we go. But for example, you can access the console right here, and you will be able to do all of this demo that we have right here, that Matt and I are showing you. And of course, we have the beautiful art of the dirty pipe spilling and polluting the waters of our penguins, our Tux penguins. And I'm going to go through the detection and mitigation portions of this particular vulnerability. So without going straight into the demo, I do want to talk a little bit. DirtyPipe is a very stealthy, at least in comparison to the last one, as Matt mentioned, in comparison to PwnKit, because it's leveraging a system call that's specifically designed to eliminate the overhead from normal file system operations, the splice system command, the splice system call. It doesn't make some of these changes that we might ordinarily have as detection mechanisms, like Matt was mentioning, the modified date timestamp. So when Matt was writing those, and I'll show you here and again in a minute when I rerun these exploits, when Matt was writing to etc password and to user bin sudo, when those pieces of data were being injected into those files, there was nothing happening to that timestamp. It was remaining unchanged. The only reason we wanted to change it back was because we did the copy out and in. We could theoretically have used DirtyPipe again to overwrite that data with the original content and have never made a trace of any overwrites to that modified time. So the real place to make these detections, because it's kind of so stealthy and doesn't use the file system's ordinary read and write calls, is I got to start with saying probably elsewhere, right? So the noisier parts of an attacker's kill chain here are going to be not at the privilege escalation. This is a very stealthy privilege escalation. So the other places that you can have your detection set up is the attacker here is this is a local privilege escalation is going to have to get access here somewhere. So that initial access step, whatever that be, phishing, drive-by compromise, web exploitation, those are going to be places where they can be detected. The establishment of C2 channel, the delivery of any subsequent stage payloads, another piece of malware, persistence mechanism. These are all places that are potentially noisier than this that you may be looking at. And then, potentially most importantly, once this privilege escalation is successful, the attacker is going to want to do something with it. So those root level commands being typed into the command line here by the attacker should absolutely be logged and be alerted on by any correctly configured security system. Okay. With that said, I think I'm going to go and jump into demonstrating how this is detected. One more note. The couple of implementations that we've shown you here, one overriding etc password, and one overwriting the sudoer file. They have different signatures that can be detected on because of the files that they choose to overwrite. The original POC code published by Max Kellerman doesn't work, interestingly, because the file that they choose to overwrite is not necessarily world readable. But there is a way to make it work, and the way that one works is to publish a new key into the authorized keys file, and to enable an SSH and to SSH to root in that method. And that would publish a log right to the SSHD log. And right there is your detection, right? You have an unauthorized SSH to your system. And the other two have different mechanisms as well. The variant 2, the first one that Matt showed you, that writes to Etsy password and allows him to SU, that uses the SU binary completely unmodified. And so we'll see that that actually logs quite normally in your auth log using SU. And then variant 3 is the shellcode injection into user bin sudo, and that won't. So here we go. I'm going to over here just do a in our Manjaro machine a journalctl tac f, which in Manjaro is a good way to, or in any Arch-based distro, is a good way to follow or to see basically all of the relevant logs. I'm sorry, I'm seeing something interesting here. Just trying to grep that out. grep tac v. There we go. That's the reason. The words here I'm grepping out are the touchegg service, which is just a multi-touch system, which is not able to communicate because it is a VM, and so it's just reporting repeatedly to the system logs, and so I'm just grepping that out because it's noise for us. Okay, so I'm going to show here all of the logs using journalctl, because in the Arch-based distros, they're all basically consolidated there using the systemd logging system. And so we're going to be able to see what does and doesn't show up when we run this exploit again. And as I mentioned, the two different attacks are going to have two different kind of profiles that we're going to see. So as we can start off here, I can just, sudo echo I am not a sudoer, entering the user's password, and we are going to see SimSpace is not a sudoer. User not in sudoers. So this incident has been reported. Okay, so that's all I wanted to show you, that this user does not have any privileges, and now we're going to get some privileges using our POC code. So I'm just going to copy and paste here so we can see this. The same attack that Matt ran, so there is no need to re-explain this. I'm just going to run it.
Looks good.
It worked.
All right.
And there we are. I am root. And we see that over here using this, I used, as I mentioned, the SU binary unmodified, and the SU binary reported as it's supposed to, that I accessed a root shell. Now, as the SimSpace user who was not in the sudoers file, this should be a huge red flag. So there we go. The second POC code that the first POC code we presented to you is logged in that manner. But you also probably noticed that as I was entering this, nothing was showing up. So during the exploitation itself, the audit daemon and everything else that is installed here to conduct security audits was silent. I'm going to head over to the Ubuntu machine and show you the second one, the overwrite of bin sudo being even more stealthy. So I'm going to just follow the journal in the same way.
I was just stringsing the POC Trojan to answer an upcoming question here, but you can go ahead and do what you got to do.
An upcoming question. All right, awesome. And real quick, we have, well, hold on. Do we have the unmodified sudo still there? Good. Okay. Matt, you did copy over the original sudo, right?
Yeah, I believe I did. You may just have to set it back to perm. Was it for? Yeah, just set the set UID binary, or the set UID bit rather.
All right, what's the, oh, I'm not root though. So I'm not gonna be able to do that. Okay, this isn't a game stopper. I'm gonna go back to the Manjaro machine and do it there.
Okay.
Okay. The POC password binary, or the Etsy password binary is still exploited, but I don't care about that because I'm going to show you the attack variant 3, the second demo that Matt did. So here we have the original user bin sudo. With the February 2nd modified date. There we are. I'm going to do all those previous steps, copy out the addresses. I'm going to do this all in one block. So just beware. You're going to see a whole bunch of text scrolling across the screen. All right. It looks like everything worked just fine. I'm going to compile and run the exploit. You see on the right, we are still running our journal CTL. And when that exploit ran, nothing happened. Not a peep. And now it gets interesting. I do want to show real quick that we have modified the binary, as you saw last time. It has a different hash. So there is 99C92. And up here, originally, we had a different hash. So modification has happened. And we are root. And nothing has been shown on the right. Not a peep. Okay, so there we have it. Your default configuration, no matter where your logs are being forwarded, because the Linux logging default configuration isn't showing anything. So this is very stealthy using the Trojan method. And since we copied out the original binary's timestamp, we can replace that binary with the original again using the backup that we made. Valid. Sudo end time. Okay. Is the local variable to the SimSpace user. That's all right. I don't think I need that anyway, because we're going to move on to a new modification. So that's basically it for the original module. Because when we released this package, there basically was no, um, you know, detection mechanism that had been adopted by the community. There since has been one, but sorry, I'm just looking over my notes as well. Yeah, those hashes you saw me take, that is to demonstrate that there are specialized tools that would have to be installed and configured for your environment. But there are tools that could take repeated hashes of sensitive system files, like those setuid binaries or those etc password, etc shadow files, and report basically when those files have changed on disk, which is again a custom configuration for your environment. And that was basically all we had for a detection mechanism until earlier this week, when a gentleman by the name of Jonas Lejon published a detection mechanism using Audit D. So Audit D is a service that can be installed. It is installed by default on our Arch distro. It is not installed on our uh, our Ubuntu distro, but I have installed it. And this can be configured to specifically listen. I'll just show you the tweet again. Specifically listen for that splice system call. And the splice system call even more so with these specific arguments that are part of the DirtyPipe exploit. So I can configure these commands to audit D. Looks like that first one did not paste properly. Audit D. Okay. I'm going to run those again. Rule exists. Okay, so it looks like they were configured. Good. So what we have here is an alert on always. I'm going to show you on the tweet because this terminal is acting up. Alert on the system call tech s splice with the arguments hex value 3 for argument 0, hex value 5 for argument 2. And where those come from are the system call made in the exploit itself. To the splice system call. So here we go. FD offset P1 null. These are what we're basically having that signature on. So this should reduce the cases of false positives because we have whittled it down to a set of splice arguments that are indicative of the DirtyPipe exploit. And now, hopefully, since we have this configured, we should be able to attempt to do this exploit again. And see on the right the demo gods are not good to me. as we overwrite. There we are.
That looks like it. There we go.
Our audit D system configuration here has alerted us that the
Nice.
splice system call was made, and that looks like it might be DirtyPipe. So
that's fantastic, because
it's
that
very
is
good.
such a low level system call. It reminds me of like when shellcode injection and process injection happens on the Windows side using the NT DLL instead of kind of the higher order DLLs. Some products will hook into the higher order DLLs, but if you perform direct system calls, there you may be able to bypass that correctly or entirely. So seeing that this sees that syscall take place is like, that's a phenomenal thing to see that defenders can do.
And that's the power of audit D. And what you just saw me mess up, and I wasn't doing a good job of talking over my console commands there. But what you just saw me mess up was following the journal as a non-root user, right? So looking at it as root, it actually is now allowing me to see those audit D logs that were put in for the system calls.
You know, we do have one other question here, which is, have any EDRs detected the MSF Venom strings?
Sure. Kris, if you're still sharing, could you cut over to the Ubuntu DirtyPipe image? I think we can just keep it on yours, but I've got the strings open.
Sure thing.
So two answers to this question. One, have EDRs detected the MSF Venom strings? I cannot answer that. If I can make some estimates of if EDR products out there are going to be catching a string of shellcode built by MSF Venom. I will not say anything definitively. What I will say is that if you, and just to do this, I'm using the strings utility against the POC Trojan, which, if you remember, I think I had the, well, in any case, I can just do a less on POC Trojan.c, the source code of this. It's important to make a distinction here that we're not really using MSF Venom to generate this payload. The exploit, well, we're using it to generate the shell code of the payload, but we're not using it to generate the binary itself. So the only place that MSF Venom comes into play is right here in this this variable, this array of shellcode bytes. Now, this doesn't make a string, however, it's unlikely that this shellcode block is going to make a string, and we can check that by stringsing the binary. And we go down a little bit and we take a look. There are other indicators that really, if I was a kind of a crafty adversary, I could remove. But that shellcode block doesn't come through in the form of a string. That's not to say that there are things that will that's not to say that there are not things that will detect those blocks of shellcode. Something like Yara, a tool like Yara, can be built to look at the byte patterns and byte arrays in a binary and pick up on if MSF Venom shellcode has been put there. I also want to point out that MSF Venom is really just one way of building shellcode. The shellcode for this exploit is really simple, to the point that I could probably write it myself using straight, hexadecimal bytes. Because really all you're really doing with the shellcode is calling bin bash. Have EDRs detected it? I don't know if I can answer that, but it's important to make the distinction that the shellcode in this exploit is set as a variable, and also may not be the shellcode that might be somewhere else in another exploit.
Excellent. I think that answers all of our additional open questions. Is there anything else, Kris or Matt, from your side that we need to show that we didn't show yet?
Yeah, very simply, the mitigation for this exploit is pretty straightforward. So Max Kellerman actually wrote the patch and committed it on the 24th of February, or just before. And all he had to do was initialize that flags variable so that it was not able to be written to by with arbitrary memory page. And all you need to do if you have a rolling distro is nothing, because the kernel channel that you are subscribed to will automatically update. I had to do custom work in that Arch-based distro to be able to disable that automatic update. And if you're running a Debian-based distro or a Red Hat style distribution, then you use your standard package manager to install a recent, since the end of February, kernel version, 5.16, 11, 5.15, 25, or 5.10, 102, for each of the release channels, respectively.
And of course, everyone's right here looking at the SimSpace portal. In our content library, we do have an entire module going through all of the DirtyPipe and both the offensive, defensive positions and mitigations, as we have here. If anybody has any questions regarding our content or wishes to get hands on with it, feel free to reach out to our team, either at sales@simspace.com or existing customers through our customer success team, and that's success@simspace.com. So again, I think that does it for all of our questions right now. Unless Matt, Kris, anything for you guys? Who you picking in your March Madness pool for sports ball?
I don't know if I have an opinion on that, unfortunately. I know that's really surprising to hear, but I don't really go much in for sports.
Oh, I'm sure Chris Webber's going for the Michigan Wolverines, right? You know, no timeout pro with none left, right?
Not taken after my namesake very much there.
All right. Well, for us here at SimSpace, thank you all for joining us. If you have any questions, feel free to reach out to us. Otherwise, please subscribe to our upcoming webinars. As we have them, we will come out. And then otherwise, secure confidently. We'll talk to you later.